Good morning. Thank you for attending. We're going to start now, and obviously, if other people join later, they can jump on. My name's Philip Humphreys. I'm the Chemicals and Chromatography Sales Manager for SLS. It's my great pleasure to introduce Egidius Maktavis from Merck. Egidius is from Lithuania. He joined the R&D department at Merck in Darmstadt in 2008, where he's currently a lead expert in chromatography product and portfolio management. With 25 scientific papers and 13 book chapters to his name, his major focus areas include multidimensional liquid chromatography, proteomics, and mass spectrometry. Just a bit of housekeeping. We've got a chat and a Q&A. Can you please use the chat for any technical issues you may have with the call? If you have any questions, please put those into the Q&A section. If any questions have been asked that are similar to something that you would like to ask or you're interested in, please like the question in the Q&A, and we will try to prioritise answering that at the end of the session. The session will be approximately an hour long with questions and answers at the end. Egidius, I'm going to pass over to you now. Thank you very much.
Yeah, hello everybody. So thank you very much for kind introduction. So without any further ado, I'm jumping on the topic, which is today we are talking about the greener liquid chromatography. So as you can see, I'm already limiting a bit the topic because the topic green chromatography or green chemistry or green analytics is very broad. So we will not have time to talk about every aspect. So that's why I will be only focusing on a liquid chromatography in this presentation. So at the beginning, I would like to talk about chromatographic materials, because without chromatographic materials, we cannot have any liquid chromatography. And I will be making my point how to make chromatography greener by using one of these several different materials. And that's why I would like, to present them beforehand and to tell what kind of advantages or limitations all of these materials has. So I'll be talking first of all about fully porous particles. This is classical material. We all very familiar with that. The biggest, of course, advantage of these materials is higher loadability. And then, of course, the next one is a trendy and newer one, the superficially porous particles. These materials has the advantage of being the most efficient type of packing in the chromatography market. And last but not least, the third one, I will be shortly presenting the monolithic material. The monolithic material is made out of exactly the same silica, like fully porous or superficially porous, just the structure is different. So instead of particles, we have the monolithic spongy structure. And because of this structure, we have much greater permeability and much lower back pressure. So this provides us a series of possibilities how we can utilize these materials without running into any problems. I will show you during my presentation. So a few words deeper about fully porous particle, and here I will present a few examples on Porosphere Star material. This Porosphere Star material is really excellent material. It has excellent peak shape. You can analyze many different compounds, also acidic, basic, also metal chelating compounds because of really very high purity of the material. It has the best performance or selectivity applicable for many different applications. Extended pH stability just because of the special end capping. It's still silica-based material, but still you can use it up to pH 10.5. And it has also excellent reproducibility because we use the master batch. So the different batches are mixed before they packed into the column. So this also makes the column to column or batch to batch significantly more reproducible. And with these materials, we have the several different modifications, several different particle sizes as well, as you will see in my presentation, and just a few evidence what I was saying. So first of all, you see that the metal content is very low. So that's why this Porosphere Star material is very good with all basic as well as the metal chelating compounds. And we run the Tanaka test, so we measure capacity, hydrophobicity, steric selectivity, silanol capacity, and ion exchange capacity of leftover silanols at 2 different pHs. And the graph is drawn in the way that the hexagon becomes bigger when the chromatographic parameters become better. So the size of the hexagon, it means that the column is better. And then when we compare with many different competitor columns, you see that our hexagon actually indeed is the biggest one. So that means that this column could easily replace all the other columns without any problem. Then another material very shortly, which I would like to also to introduce, is fused core technology, or a superficially porous material. This one has the very clear advantage, as I already briefly mentioned, is the superficial efficiency. So efficiency is really significantly higher, and this then also is the big advantage for chromatography. And you can see how efficiency plays the role in separation. So first of all, when we reduce the particle size, efficiency, of course, is increasing. But if we just keep even the same or similar particle size, but you change the technology, so instead of fully porous particle, you create a superficially porous particle with solid core inside, you see that the resolution has a significant jump, and efficiency also has a significant jump. So this also, such more efficient materials also provides a very strong advantage for chromatography, because immediately your resolution is better, your peaks are higher, your sensitivity is higher, and so on. So the long list of advantages then related to this type of material. And then the last material, which I would like to go a bit deeper, is the monolithic. So here you see the structure. So as you can see, no particles, just the structure. We have the pores inside the structure for flow through. The skeleton is also porous, so the molecules can come into the skeleton, interact with functional groups, and then we have a retention, and then we have a potential separation. And then these materials, then of course, we don't have particles inside. So sometimes it is difficult to understand what another column can do for us, how the chromatography would look like. So in this case, I created this table. So here you see the relative particle size, just for you to know what kind of efficiency you can expect from the material. And you can see that these materials provide higher efficiency. So they act as the smaller particle pad column, but they generate pressure like a bigger particle pad column. So this is a very good, a very big advantage, because all what we need in chromatography is efficiency. Pressure, it just comes as the pay for our wish to have more efficiency, actually. But in this case, efficiency is like small particle pad column, and the back pressure is like bigger particle pad column. So we can really benefit from these materials. And then, of course, this material is very stable, because when we have the particles inside column, we have to have a fritz. Fritz will act like a filters, so they could get clogged and so on. So particles has a tendency to move. So that's why the column is also one of the aging mechanisms of the column. And once you have the monolith, the structure is frozen, the permeability is high, so structure really does not change with the usage. Pressure stress, no pressure stress, column dry, wet, it's nothing really matters so much for the monolithic material. So that's why this monolith materials has the really long list of advantages, like really could be a rapid separation, so we can speed up the analysis. The back pressure allows us. We could use what is very important for green chromatography. We could use the more viscous mobile phases, because the back pressure is low, so it allows us. We also can use the rich matrix-rich samples and also skip some sample preparation, but it's also essential for green chemistry in general. And the lifetime normally is longer, so we can also expect less pollutants, because the column simply will work longer. So these are all very important advantages of these materials. So now I'm moving to our topic, so green chromatography. So first of all, there are several ground rules. So I want to make like a statement that in this presentation, I will follow, first of all, 12 principles of green chemistry, which was put together by Anastas. What are these principles? Without go deeper, like avoiding derivatizations, think about every step what you do, and not only consider the greenness of individual solvent, but all the mixtures, transportation, packaging, and so on. And then, of course, there are deeper rules. These rules are adapted also to analytical chemistry. So here you see also the paper, green analytical chemistry. The few rules are like that avoid sample preparation as much as possible. Watch the consumption, watch the lifetimes, and so on. So I'll go deeper. And there is also a very nice review paper by Justina. It's called the green chromatography. And in this green chromatography, it's also a lot of different advices how chromatography could become greener. So I will try now to go from a very practical perspective, and I will show you what actually we can do and how these materials which I just presented could help you also to achieve greener chromatography in your lab. So first of all, we continue with the ground rules. So first rule is that we have to watch all components in chromatography. So it is insufficient to take only one mobile phase, which is green, and then mix it with non-green, because that's what we normally do in chromatography. We use water, for example, acetonitrile. So water is green, acetonitrile is not green. Once we mix them, we generate waste, which is not green. So such type of chromatography is not considered to be green. So it doesn't matter which of the solvent A or B is greener, is still waste, is not green. So this is not a green chromatography. However, even if we use the A and B solvents, if you use the gradient, for example, and both of them are green, but if you inject your substances, and your substances are either dissolved in non-green chemicals, or your analytes themselves considered to be toxic or radioactive, for example, they consider to be really big pollutants. And then, of course, depends on how much we inject, but it's also very likely that we will not really have the green chromatography because our waste potentially is already contaminated with our injection. But this is a bit a thin line. So it really depends, as I mentioned, what you inject and how much you inject as well. And the only real, absolutely green chromatography is in the case when we have all our solvents are completely green, all what we are injecting and the solvent which we're injecting is green, and only then our waste is also completely green. So this is a completely green chromatography. So we might have the different levels of how our chromatography green is actually. So now to achieve greener chromatography, and I'm not talking about immediately a green chromatography, because to achieve green chromatography is quite difficult, and maybe in some cases not even possible. So we are talking how just to become a little bit more or less greener. And this is possible to achieve with the 3 R's, so-called 3 R's. So replace, reduce, recycle. And also these 3 different strategies, they could be mixed in different combinations together. And also then, of course, when we mix them together, the effect is actually then cumulative. And then we get even to greener and a greener chromatography at the end of the day. So now I will go one by one, and I will talk more deeper into these all 3 different strategies. So first of all, one of the simplest one is recycle. So recycle could be used when you run isocratic chromatography. So that means that your mobile phase does not change with the time. So this is the first requirement. The next requirement must be also that we do not have too many peaks. Our baseline is clean, and the peaks has the significant distances in between. So it looks like that we have the plenty of solvent wasted between all these peaks. So that means that if I'm installing switching valve, potentially I can direct all this flow between these peaks back to my main bottle like that. So, and from that perspective, my waste generation will be significantly decreased. So at the end of the day, I will have a ratio between my white part of the chromatography, where my peaks are eluting, and this green part of the chromatography, where I'm recycling my mobile phase completely. So this approach works quite nicely. But as I already mentioned, the limitation is isocratic type of chromatography. The second point I have to make, that with the time, I cannot recycle for ages. With the time, I still will accumulate the pollution with injection. And then my solvent at one point or another will have to be replaced. That's one consideration. And then another part is that if you see such type of chromatography, this also shows that there is the problem with method development as well. So is there also a possibility to develop method in a way that these peaks are eluting closer to each other, and then we will not need to recycle. But the recycling is an option if you have such a picture and if you don't want to rework your method. So now we'll go in the next step, which called reduce. And also, as you can see that on the left side, we are talking about the method changes, which does not require really to change anything, because recycling does not really require to change the chromatographic separation for me. Reduction also does not. So how I can reduce my solvent consumption during my chromatography? So there are two approaches. So first of all is the column length. So if I have the short and shorter column, then of course shorter column provides speed, so I have fast analysis, and also solvent consumption is lower. If I have the longer column, then of course my resolution is better, but my solvent consumption and the time needed to run chromatography is longer. So I would like to demonstrate you an example, and this is by using the monolithic material. So here you see the 10 centimeter column by 4.6, and then I have a 50 centimeter, 5 centimeter column by 4.6. You can see that my analysis time is actually halved. So every time I halve my column length, I have the analysis time, and also my solvent consumption is also halved. So this is a significant savings, significant improvements, or significant reduction of the solvent consumption. But also what you can see that my efficiency, of course, is falling down. So I'm losing my resolution and I'm losing my efficiency. So now in this case, with the running the same standards, as I showed in my previous example, this is absolutely okay. However, if I have the real sample, and here I have the real sample, so this is now is a sun lotion analysis, and then you can see that with this column, 10 centimeter column, I had the baseline separation here. So now I don't have it anymore. So this approach only works if you have the exceeding amount of the resolution, which actually you can trade for the greenness of your chromatography. So you can compromise your resolution, but then you gain the savings. But if you are really analyzing complex sample with a lot of peaks, then this might not be the best option for you to save in that way. Then another option is of course to reduce the column internal diameter. So when we reduce the column internal diameter, there are a few things happening. First of all, the solvent saving is enormous, and that you can see approximate solvent consumption per day. So every time when we use the smaller and smaller column ID, you can see that the solvent consumption really goes down significantly. So for example, if I use only 20 micrometer ID column, my solvent consumption per 24 hours is only about 30 microliter. So this is only considering that my pump is actually syringe type pump, pumping continuously and not using the flow splitting. Most of the instruments, in order to deliver such a low flow reproducibly, actually pumps significantly higher amounts of solvent, and then they use the flow splitting, and then is not considered really to be greener from that perspective. But if you use the syringe type of pump, then definitely the savings could be really significant. And also, it's not only solvent you're saving by this, you get also a bonus. that your peaks become narrower and they become also higher. So that means that you're zooming into your limit of detection and limit of quantification, so you can see lower and lower concentrations. So this is also an important add for chromatography. And if you move from 4.6 millimeter AD to 2 millimeter AD, solvent savings could be quite significant. Like in this case, we only use 1/5 of the initial solvent consumption. And as I already mentioned, this could be even acetonitrile, so that means that you will use less toxic material at the end of the day, will generate less waste, so our chromatography will become greener. But even if you use already a green mobile phase, like for example ethanol, you still may save it and still generate less waste, even if it is green. And I would like to show you a few examples. So this is an example with bioshell. So this is a superficially porous material, which I mentioned. This type of material has absolutely highest efficiency. So you can see very nice separation, a lot of very sharp peaks. And moving from, for example, 2.1 millimeter ID, we can move even further to the smaller column IDs. And in this case, from 2.1 to 1.5 millimeter ID would easily halve the solvent consumption. So that means that also our chromatography becomes greener in this perspective. Another approach is, of course, to not only to use the shorter columns, but for example, if you have a problem with the resolution, so you cannot trade resolution, you cannot lose efficiency. In this case, what you can actually do, you can reduce the particle size, and by reducing particle size, your efficiency will increase. And at the same time, of course, if you don't need this high and high efficiency, then we can reduce the column length. And once we are reducing column length, then of course we are gaining efficiency with the smaller particle size. We are losing efficiency with the shorter column, but at the end of the day, it's a bit similar still. So my separation does not lose too much resolution. But my chromatography becomes significantly faster. And once the chromatography faster, my solvent consumption is significantly lower, because here I need to pump 16 minutes through my column. And in this case, I only need 4 minutes. So 4 times my solvent consumption will go lower. And as you can see now, efficiency slightly still dropping, because my particle size does not provide me so much more efficiency compared to reduction of the column length. But nevertheless, I still have quite high efficiency. So it means that my resolution is still baseline. So on that, what is the most important. So let's see the real example I will show on this beautiful porous star material. So here is a standard analysis, 150 by 4.6. This is one of the most used column globally still, 20 minutes analysis, including recalibration. So we need about 20 milliliter per run. If we move this to 50 by 2 millimeter column, we only need 2 minutes, including recalibration. So solvent consumption is 2.2. So in real life example, we see that we have a speed up. We are saving a lot of time. We have a speed up by factor of 10, and we have a solvent consumption dropping by 10 times. So we only use 1/10 of the solvent compared what we used in the first example. And this is relatively easy. And what I showed is actually the moving HPLC to UHPLC. And there are actually formulas given, and it's also allowed by pharmacopoeias to make these changes and so on. So you just have to follow the formula. So and immediately you can see that my flow rate is significantly reduced. My analysis time with a shorter column will be significantly reduced. The gradient time also could be adjusted and so on. So I can really speed up my analysis and consume lower amounts of even acetonitrile, if that is my method. But with such change, I don't have to change anything. I don't have to revalidate, because this is allowed by pharmacopoeias. And would like to give you another example using the photosphere star as well. So here we have a separation of the several compounds. And then once we do these recalculations, which I showed in the previous slide, so immediately we can say 45% time, 85% solvent in this case, according to USP requirement. And this is also, we are saving a lot of solvent, a lot of sample, which we're injecting. So if the sample is precious, this is also helps to reduce it. And analysis time is definitely significantly shorter. And using UHPLC, I can even increase the flow rate and my chromatography could become even faster, but my solvent consumption doesn't change. So solvent consumption per analysis stays the same. So I'm not increasing the greenness of my chromatography, I'm only saving additional time. So now one consideration, one part from the troubleshooting, that it is okay to move to smaller column IDs and to smaller columns. All what you need to watch the dead volume, dwell volume. So that means that it is relatively easy to lose efficiency if you have any unnecessarily larger volumes in your capillaries, in your injection needle, and so on. And this could ruin your efficiency quite significantly. So you can see in this example how 10 microliter volume, which is added onto analysis, can actually reduce plate counts from 43,000 to 36,000 theoretical plates. So this is a significant decrease. So this gives you an example how important is that. And also it's not only the efficiency which could actually suffer from the dead volume, but also where this dead volume exists. And the general rule is that the dead volume after the separation, after analytical column, should be really kept at minimum. So even if you have to use the longer connection capillaries, because, for example, of mass spectrometry, so you need to have a certain distance between the instruments. So it's always the better choice to have the connection between autosample and the column should sit directly in front of the detector whenever it is a diode array or mass spectrometry, and not vice versa. Because if you have the connection capillary after the column, your separation you're achieving in the column is actually ruined in your long connection. So please keep in mind this as well. Also, as I already mentioned, the moving to, first of all, according to the green chemistry rule, sample preparation should be minimized. This is number one. Number two, if we move to smaller particle sizes and smaller column IDs, it is easier to clog our columns because they're simply smaller particles inside. So that means that if you're moving from the classical to the really miniaturized UHPLC type of chromatography, and your sample is not super clean, quite often you have to increase amount of sample preparation. It is necessary in order for your column to survive. And this is not according the green chromatography or green analytical chemistry rule. So the better option would be that we change maybe the material, the chromatographic material. In this case, I would recommend to use the monolithic phase because it's a little more forgiving towards the dirtiness of the sample. And then at least to not to increase any sample preparation steps in addition, because this is actually is opposite what green means in chromatography. And I would like to show you one example how it is actually done. So in this case, we have the company which actually implemented the monolith in the work stream. And first of all, they managed to shorten analysis time because they were speeding up the analysis. And also what's important that they managed to skip sample preparation completely. So this is one big checkpoint for how to become greener in chromatography if you're able to skip sample preparation completely. And then by skipping sample preparation and also shorter chromatography, then immediately leads to significantly lower solvent consumption. So this is also a big advantage then to make your chromatography greener. And then another example which I would like to show with UHPLC. So we replace the particulate material with the monolith material, and you can see the separation is quite similar. And at the same time, we managed to reduce the sample preparation time necessary. So we are not able to skip the sample preparation completely in this case, but at least we're able to reduce it. And by replacing the column, reducing the amount of the sample preparation necessary, the chromatography becomes greener from the sample preparation perspective as well. And also, monolith, as I already mentioned, always has a longer lifetime. So that means that waste generation from replacing one column with another is also reduced. So now I would like to talk about other solutions. And these solutions now include replacing the mobile phase completely. So that means that we are going to try to eliminate any toxic or any non-green solvents from our chromatography. And I will discuss how it could be done. But first of all, I have to mention that if your method is validating according to Pharmacopoeia, you cannot do that without being obliged to have the full revalidation, because in none of the pharmacopoeias actually allows to change the mobile phase composition. It is only allows to change slightly the concentration, the composition, but you cannot replace any component with another component. If you do that, then immediately you have to do full revalidation. The second is that if you replace one solvent with another, it's still chromatography. It's still absolutely necessary to have the highest purity for solvents. So we cannot simply take, instead of ethanol, take the simply vodka, because the vodka from the shop, the baseline noise would be significantly higher. The baseline drift also will be significantly higher. And I'm not talking in this case that we absolutely cannot connect such a not well-prepared solvents with mass spectrometry, because mass spectrometer then would be polluted. So if we change one solvent with another, we still have to have isocratical grade, gradient grade, and mass spectrometry grade solvents to be ready. And then the few other important aspects. So once we decided to change our mobile phase or mobile phase components completely, of course, we have to be ready to have the really drastic effect on selectivity. So we'll need to have the selectivity optimization again. Then, of course, once we change the mobile phase, then we have to make sure that all compounds which we're injecting on the column actually could be eluted. Because please keep in mind that what we see as the outcome from an analytical column is that what elutes out of the column, but it is not always exactly the same what we injected. So some compounds, if they got so sticky and if the mobile phase conditions is not right, they could stick irreversibly to the column, and then they could stay inside the column, and then we will never see them in the detector. So we need to make sure that we elute everything whenever we inject on the column. And then, of course, once we replace acetonitrile in particular, then UV cutoff or mobile phase transparency plays the big role, because the acetonitrile is really good with that. Acetonitrile could be used really at the low UV range, even from 190 at 200. It has quite low adsorbance. That means that, and all other mobile phases, all other alternatives, they don't have this low or high transparency and low UV cutoff. Then also acetonitrile has quite low viscosity. It actually has the lower viscosity when mixed with water than the pure water. So that means that viscosity might be also an issue. So the back pressure definitely will rise. And that's why the monolithic material could be an option if you tend to use the high viscosity mobile phases, and then the back pressure would be too high, because the monolith higher permeability, that would be more forgiving. And then, of course, the compatibility with chromatographical system. So with everything, with column, with Fritz, with the connections, and so on. So with every part, where the mobile phase actually touching any surface, all these surfaces has to be compatible with your new mobile phase composition. So this is also important. And then one of the last considerations, important consideration, is that you still have to, with your new solvent, you still have to be able to dissolve your analytes. Sometimes it is not so easy. Sometimes it's a problem. And then, of course, we need to think about the toxicity for human, for nature, because we're working in the lab. Also safety, vapor pressure, explosiveness, flash points, how easy it is to transport from one place to another. And then when we talk about the greener solvents, we shouldn't forget the packaging and transportation distances, because it really makes no sense to make the super green solvents somewhere very, very far from our lab, and then to transport it overseas a very long distance. So the all greenness of this approach that could be gone just because of the transportation. So these are points to consider. And then, of course, selecting the different mobile phase. As you can see here in the table, there are many different options, of course. But the point is, what I want to make there with this slide, that the selectivity definitely will be different, because every mobile phase you will choose, they will have a different parameters, different elution power, and so on. So that means that the selectivity definitely going to be different. So that means that you will need to do the method optimization again. And the method optimization could be done. One way is using the Lloyd Schneider's triangle. So that means that we are using the several different mobile phases. We make mixtures of these, and then if you run the analysis, then immediately you can see that your separation will look completely different depending what kind of mobile phase actually you choose. And then this is a starting point. Then you can see which one to pick, and then further to develop. So the method development should be done in the similar way. And in this case now, I would like also to show that how acetonitrile could be replaced with methanol. And I understand that methanol is still the same toxic as acetonitrile, so it does not fulfill the toxicity. However, thinking about the nature, methanol is considered to be a greener alternative compared to acetonitrile, because it's decomposed easier by microorganisms compared to acetonitrile. And if you're replacing acetonitrile with methanol, then of course, because that elution power is lower, so you can see that we have to increase by a couple of percent methanol concentration in order to match our separation. So this could be done relatively easy. In not 100% cases, I would say maybe about 80% cases, the methanol could be a good alternative. And of course, the much greener alternative would be, of course, ethanol, as you can see in this case. And ethanol could be actually quite nicely used. However, the separation most often will look different, as you can see now in this case, but there are possibilities using this high efficient column, Ascent Express, superficial pores, which I mentioned at the beginning. Then actually you have a chance to improve slightly, but you can see very often it is still not possible to obtain the same separation with ethanol as we had with acetonitrile, but it could be somewhat similar. And then would like to show you another example, acetonitrile versus ethanol. And in this case, we use the monolithic column. So in this case, we analyze in beer. So we are looking for this hydroxymethyl furfural, which is the cancerogenic compound, and it's formed when the sugars decomposed at the temperature, decomposition of sugars. It's also the same compound is a nice indicator for honey. If it was temperature treated or not, and it has to be monitored, as I already mentioned, because it's cancerogenic. And you can see now using acetonitrile, we couldn't have the nice separation, so we can actually see we are separating this HMF. And then if we move it the same separation to ethanol, we still can achieve a similar separation. So we still can see HMF in the run. What I already mentioned, that of course acetonitrile has a lower viscosity, so you can see the back pressure is lower. Moving to ethanol, the back pressure is increased. So then it means that you should use some lower pressure columns, like for example monolith column, if you would like to adapt to this method. And also another point, acetonol replacing with ethanol also would require slight increase in the concentration of ethanol in order to maintain elution profile in similar way, or capacity factors for different compounds. Of course, at the same time, also what is possible, it is possible, what I already mentioned, we can reduce also column internal diameter. And by doing that, our method then also will become greener. So from, like in this case, from 20 milliliter solvent per run consumption, it could be reduced to 2 milliliter solvent consumption per run. So this is also would be a significant improvement. And in general, I spoke about the methanol a bit. I mentioned that in most of the cases, it could be a useful solvent, and it is considered greener, at least greener than acetonitrile. Is still the same as the same similar toxicity compared to acetonitrile. But methanol water mixture could be used for many separations, like for nonpolar compounds, even for basic compounds, for acidic compounds, metal chelating compounds, and so on. And everywhere you can see you really could have the nice separation. And I show another example on the monolith using the methanol, and in this case you can also achieve really a fast separation as well at the same time. So what are other alternatives and other considerations? So first of all, other considerations. So as I already mentioned, UV transparency. So acetonitrile has the lowest or the highest UV transparency. So other solvents, as you can see, have a significantly worse. And there is the general rule in chromatography that transparency should not be you cannot lose because of the solvent more than 20% of your light. So transparency at least has to be 80%. And you can see that depending on the wavelength, this solid red line cuts a lot of solvents actually. So you can only use not all of them. So that means that if you really need to analyze at the low UV range, that means that you cannot really take, you don't have so many options of choosing the different solvent and acetonitrile. So in this case, that would mean that you really would need to go to not replacing, but recycle or reduce in this case. And also, please keep in mind that it's not only the mixture, but also additives plays a role. Like, for example, this TFA in water, TFA in acetonitrile. You can see that curves also are different, and they have the significant cuts. So you can only use them below this line. So that means that only above 230 and more nanometer. So this is also important consideration. And of course, the wavelength you need to select according, depending on your compounds you're analyzing. So for different compounds, we have a different absorption intensities. And then, of course, the best is, of course, to use the absorption maximums. So like in this case, 220 or 260 in order to have the sufficient sensitivity for your compound. So you have to match these two parameters. So you have to look in the absorption curves for your compounds. You have to look how transparent is your potential mobile phase at this wavelength. And then you can see, can you use it or not. And then, of course, what I'll also mention, the viscosity plays the big role. So the acetonitrile viscosity is actually the lower. All other options, ethanol, methanol, or isopropanol, and so on, they will have much higher viscosity, so the back pressure would be significantly higher in this case. So you need to watch it out as well to make sure that the column is not damaged by extra pressure. And from that perspective, the monolith also could be a good option. I also mentioned that the compatibility with all the parts in the chromatography instrument should be also matched. So that means that, for example, you cannot use the peak column hardware or peak connection. For example, if you run dimethyl sulfoxide, for example, and some other solvents. But in general, there are no limitations for many solvents, but you have to check for column and for your analytical instrument as well to make sure that the change of the mobile phase does not damage your instrument and the column itself. Are there other possibilities to how to make your chromatography really green? Yes, they are. And one of them is actually there is a possibility to use the soaps. So, and in some cases, you can eliminate the necessity to use organic solvent completely, like you see in this case. There is an separation on the cellulose triacetate using only aqueous mobile phase. So in this case, I use the sodium dodecyl sulfate. So nothing else. A bit higher temperature and soap in the mobile phase, and you can see that the separation is actually possible. So we separated two enantiomers relatively easy. There are more such examples also in the literature we can find. And here we have the 3 antibiotics separated only using the 2 different surfactants, sodium dodecyl sulfate and this Bre35 surfactant, and you can see that the separation is done baseline in also relatively short amount of time. Also, what is important that we do not really compromise the limit of detection or limit of quantification. So these are stays really high, and the method becomes really greener because we eliminate the complete usage, for example, of the acetonitrile or organic solvent, and because the monolithic material is used, also the solvent, the sample preparation steps also has been reduced. So that's what this means in the middle of this GAPI evaluation. And GAPI is one of the several different tools which could help to compare how green is your chromatography. And of course, the more green color you have in this diagram, the more green. And there are several different aspects it's actually touched. So this is branch for sample preparation. This is branch for reagents and compounds. This is for instrumentation and so on. And this is for the sample manipulation. So you can see that there's several different perspectives how you can make your chromatography greener. Also, another relatively green type of chromatography is a supercritical fluid chromatography using CO2. But it depends actually what kind of additive is used. In this case, it's methanol, so still considered to be relatively green. If it would be ethanol, it would be even greener. But there is also in the literature, there is certain concerns. It really depends where CO2 is coming and what is the money consumption to produce the CO2 to make sure that by producing CO2 we are not consuming too much energy, because it's actually is purified by cooling down the air or by collecting the fermentation, the CO2 released during the fermentation. But the supercritical fluid chromatography in general could be considered as a greener type of chromatography, and also is very powerful technique. As you can see now, many nitrosamines are separated in one single run in a relatively short amount of time, because normally supercritical fluid chromatography is a quite fast technique because of the higher diffusivity of the compounds and the much faster mass transfer kinetic. There's another option how to make your chromatography really green is to increase the temperature and use water. So water, if it is in superheated state, which is from at the high pressure as well, from considered to be superheated state from 75 degrees to 180 degrees approximately, and then using the pure superheated water, you can actually separate some compounds. So superheated water also becomes as the good elution power containing mobile phase and could replace acetonitrile. So in this case, you can see that as was been transferred into two fractions at 180 and 200, and then the separated on porous graphitic carbon column. Because in this case, we have to use column like porous graphitic carbon column without the functional groups, because normally functional groups like C18 or C8 or whatever are not really stable at such a high temperature, so column lifetime would be very short. So by changing the column completely to porous graphitic carbon column, we actually can use this technique and get the benefit of superheated water. And then in this case, my separation is really then green, because I'm not using any organic solvent at all, only pure water. And when now I'm talking about mentioning this porous graphitic carbon, which I showed in the previous example, we also have this material in our portfolio. So this is, as I already mentioned, this is a pure porous graphitic carbon, no modification. And because of that, it has very high temperature stability. It could be used up to 250 degrees, high pressure stability, and so on, high pH stability as well. So this material is really a provide very big advantage for us if you really would like to try the different harsh mobile phases, more green mobile phases, but harsh to our column mobile phases, and then like in this case superheated water, and then we can have nice separation. And by the way, these porous graphitic carbon columns, they could be used to separating many compounds, because the interaction mechanism includes the pi-pi interaction. So that means that any phenyl ring containing or aromatic compounds could be easily separated. We also have the separation by polarity, either induced polarity or existent polarity from the molecules, and also some cation exchange and anion exchange properties as well. And you can see that a difference from the C18, that if we really have the phenyl ring containing compounds or aromatic compounds, these aromatic compounds are significantly longer retained and could be separated quite easy, even in the better way than compared to C18. And also this type of material has a very high shape selectivity. So like in this example, you can see ortho meta para compounds could be really easily, quite easy separated on these columns. And of course, one of the strengths of this material as well, that they could be used with many different organic modifiers, organic solvents, and because there's full compatibility. And you can see this is the part of the method development. So once they're replacing one solvent with another one, you really can affect your separation in great extent. So at the end of my presentations, I would like to summarize that greener chromatography, yes, indeed, it is achievable goal. We can do actually by utilizing any of these R's, replace, reduce, or recycle. Please also keep in mind that actually we can mix them or combine these together to increase the effect, overall effect. So then we really become a greener and greener at point. And also to achieve that, we cannot achieve this without perfect or excellent materials. Such materials like Ascendis Express, superficially porous material, help really to achieve the highest efficiency, as I mentioned. Monolithic materials could provide you many benefits, a lot of flexibility points because of the higher permeability and a lower necessity for sample preparation. So sample preparation steps could be removed, and this is immediately leading to greener analytic because the sample preparation considered to be quite solvent and quite not so green type of analytic. Also, porous star material could provide you high efficiency as well, and we have several different particle sizes, so this also could help you to achieve the greenness of chromatography. And last but not least, this porous graphitic carbon column could give you additional benefits, because you can use the superheated water, you can eliminate organic solvents completely, and also you may try many different organic modifiers or mixtures of these on this material, because it has such a high stability of this material. So, and I would like to thank you for your kind attention. And if you have any questions, or if you would like to raise any points for discussion, then I would be happy to take it with you. So thank you.
Thank you, Egidius. That's absolutely fantastic. I don't think we've had any questions yet, but maybe we'll give people a couple more minutes in case they want to ask. If you're having problems with the Q&A, please do use the chat if you're having issues with that. One thing that I thought was interesting, Egidius, was there's a push in the market to go to faster and faster chromatography with these expensive high pressure machines, and actually we're saying monoliths perhaps are better on perhaps normal pressure machines. Is that correct?
So actually, it could be used in the both ways. So the monolith could be used also in these high pressure machines, because the high pressure machines, they're not necessarily high pressure machines if you install the column, which does not generate too much pressure. So your high pressure machine then becomes a lower pressure machine without compromising the separation itself. So this is the one option. And also the second option is, of course, still to use the regular machine and press a bit the limit. If you really need the higher throughput, then you still may increase the flow rate, and then you can get the higher throughput. But then, of course, the solvent consumption per time is increasing once you increase the flow rate, but the solvent consumption per analysis then stays the same. So, and we have to, in order to be fair, we have to calculate the solvent consumption per analysis, as well as the solvent greenness or method greenness per analysis, because this is only fair comparison. So yeah, monolith could actually provide many flexibility points, and this is one of them. Then you can actually choose which to use. And by the way, even the standard chromatography instrument could be still tuned. And by tuning, there are possibilities to reach high efficiencies, which then would be becoming closer and closer to UHPLC type of separation. So there are several different options in chromatography, actually, how to improve from looking from different type of perspectives.
Brilliant, thank you. I don't think we've got any other questions. So I guess the only other thing just to mention to everybody on the call is, in the next couple of weeks, SLS will be launching a priced promotion on Purostar and Chromolith columns. So we will send you information on that shortly, and it will also be on our website. If there's anything else you need, please do feel free to get in touch. And thank you again for everybody for attending, and of course to Egidius for your time and for attending and preparing this webinar. It's absolutely fantastic. Thank you.
Thank you very much.
Thank you. Thanks all. Have a great day.
Yeah, have a nice day. Bye.
Thank you. Bye then.